Okay, so 7.5 day 2, we're going to kind of talk about the difference between binomial and geometric distributions. So we're going to start off by by asking where are all the great princes. We're not going to go through and do all of this. I just want you to kind of see the difference between the two. So the piece-up young lady is looking for the perfect boyfriend. Can't seem to find them at Salem, Canton, or Plymouth. However, they did notice that a lot of frogs have been hopping around. They really don't care about these frogs because it's better to not have a boyfriend than to have a frog as a friend. But the word got out that some of these frogs were indeed handsome princes. Now the bad news. To find out which frog was a handsome prince, the young ladies had to kiss the frogs. The probability that given a frog after being kissed turned into a prince wasn't too bad. 40% of the time, the frog on the spot turned into a handsome, loyal, and faithful prince. So let's look at some situations to help out the young ladies. So what's the probability that given a young lady kissing the first 10 frogs that she sees will have 6 princes? So this is binomial. You're looking at the probability x equals 6, right? That you'll get 6 princes out of 10 frogs. So it'd be 10c6, 0.4 to the 6th power, 0.6 to the 4th power. So it's about 0.115. I could do a simulation. Again, we're not going to. But I could do randint from 0 to 9, and I would want 10 numbers at a time. 0 to 3 would mean I'd get a prince. 4 to 9 would mean I'd get a frog. So then we could count and figure out the percentage there. So this was all binomial. This is a binomial situation. Now, obviously, you don't want to actually kiss 10 frogs. So you may have to kiss a few frogs before you get a prince. But one would think once you start the process, you would keep going until you get a prince. What's the probability you'll get a prince on the first kiss, on the second kiss, etc.? So if I were to simulate this, I would do randint from 0 to 9, but I wouldn't put a number of trials there. 0 to 3 would still be a prince. 4 to 9 would be a frog. But I would stop when you get a number 0 to 3. I wouldn't actually keep going. So this is considered geometric. So if I think about the formula, the probability I get a frog on the first chance is just 40%. The probability I get a frog on the second chance would be, well, I got a frog the first time, and then I got a prince the second time. So 0.24. The probability I'll get a prince on the 8th kiss, that means I had to kiss 7 frogs, so 0.6 to the 7th, and then I got my prince. So 0.0112. So the probability x equals n would be 0.6 to the n minus 1 power times 0.4. So this is a geometric situation. So on the next page, let's actually just start our notes on geometric. So in the case of a binomial random variable, we are interested in the number of successes and a fixed number of trials. However, there are times where we are not interested in the number of successes, but how long it takes to achieve one success. So let x equal the number of children in a family that stops having children when they have their first boy. So variables are like this are called a geometric distribution. In this case, the number of trials is not fixed. That's the only difference between geometric and binomial. So the possible values are 1, 2, 3, and it's infinite. Also in this case, 0 is not a possibility. So you could flip a coin till you get a tail, roll a die till you get a 3. Technically, theoretically, it's an infinite set. Obviously, you would stop at some point. So, properties of a geometric experiment. Each observation falls into one of two categories, success or failure, just like binomial. The probability of success, p, is the same for each observation, just like binomial. The observations are all independent, just like binomial. But the trials are performed until success is achieved. This is the only difference between binomial and geometric. So, let's change this. Suppose that, because 40% is the same as what we had for the frog prince thing. Suppose that 30% have type A blood and donors arrive at random to a local blood bank. What's the probability the first donor will have type A blood? So x equals 1 is just the same as your p-value. What's the probability the first donor will be in the second one? So x equals 2. So that means the first person walked in, didn't have type A blood, now the second person does. So 0.21. Third donor, x equals 3. So that means 2 people walked in, they didn't have type A, but the third person did. So 0.147. What about the fourth? So again, 3 failures, and then my success. So the nth donor, x equals n, would be 0.7 to the n minus 1 power times 0.3. So there is a formula, and again, they're on the formula sheet. So it actually looks a little bit different on your formula sheet. So let's write it the way it looks in the formula sheet. So the probability x equals n is equal to 1 minus p to the n minus 1 power times p. So again, this is on the formula sheet. And then the mean for geometric is 1 divided by p. You can ignore this table. The variance would be 1 minus p over p squared. So the standard deviation ends up being the square root 1 minus p over p squared, which the formula sheet changes to the square root of 1 minus p over p. So, oops, that's just squared. No. Just kidding, it's not. So these two are on your formula sheet along with the mean. So again, this is our chapter 7 sort of table. We did this in 7.4. We did this yesterday. So here's geometric. So then that's finding the individual probability, finding the mean, finding the standard deviation. And then there's one more formula. This is not on your formula sheet. This works out if x, it takes more than n trials to see the first success. So you roll a die until a 3 is observed. Find the probability that the first 3 is observed on the 4th roll. So x equals 4. So that means I didn't get a 3 times. Then I did. So 0.0965. Mrs. Ginta desperately wants to have a daughter. She's going to keep having kids until she has a daughter. Find the probability she will have fewer than 7 kids. So that's the probability x is less than 7. So think about that, 6, 5, 4, all those added together. So you can add them all together, or I can use this greater than rule. I can do 1 minus the probability x is greater than 6. Because again, I'm not going to count 6. X being greater than 6 would be 7, 8, 9. So to do less than 7, I'm going to do 1 minus more than 6. So I'm going to do 1 minus 0.5 to the 6th power. This is a rule from up above, and then I'm doing 1 minus. So 1 minus 0.0156, so 0.9844. This is kind of a hard problem. You really have to think about this part before you can get the answer. Now, if you wanted to do 6, 5, 4, 3, 2, 1, add them all up, that's totally fine. Just takes longer. From the Great Princes, find the probability that a female will have to kiss at least 3 frogs before they find a prince. So again, x is greater than or equal to 3. So that would be 3, 4, 5, infinitely. So I'm going to do, again, it's infinite. So I'm going to do 1. No, I'm not going to do that. I'm not going to do 1 minus. I'm going to do the equal to the probability x is greater than 2. So I can use this formula. So if x is greater than 2, that doesn't include 2, so it starts at 3. Which is kind of hard to say. So 1 minus 0.4 squared, so 0.6 squared, so 0.36. You could always do, this is what I was thinking in my head, 1 minus the probability x equals 1 minus the probability x equals 2. So you could do that too if you wanted. But not, you don't have to. Find the expected number of frogs a female will have to kiss before one turns into a prince. So that's the mean. So 1 divided by 0.4, so 2.5 frogs. So that's really it for geometric. Again, the biggest difference is that you stop once you get a success. So when you're reading the problems from 7.5, you really have to look at, do I have a fixed number of trials, do I not? Again, we're going to take a day or two and kind of go over this before I give you a quiz, because this is kind of a hard section.